Assalamu alaikum and good afternoon everyone. Today, we continue our lecture with new topic. Main chain liquid crystal polymers. These are the learning objectives for this topic. Students should be able to identify and classify the liquid crystals type by looking at the structure and design of the monomer. And, for today's lecture, students should be able to understand the structure and properties relationship for main chain polymer liquid crystals. Besides, students should understand why main chain polymer liquid crystals can be used as a high-strength fiber. First of all, let's see the introduction of liquid crystal polymers. Liquid crystal polymers are polymeric systems that exhibit liquid crystalline phases. Liquid crystal polymers can form liquid crystal phases such as nematic, chiral nematic, if it is based on a cholesteric mesogen and smectic phases. Just similar to non-polymer mesogens. These types of materials are very interesting because of the combination of polymer-specific characteristic plus the anisotropic physical properties. The polymer-specific characteristics such as elastic, very resistant to chemicals, low density, and many more. The anisotropic physical properties. It has many of the physical attributes of a liquid, but its molecular units are sufficiently ordered to give rise to some anisotropy. Most notably in their optical properties. The type of materials that showing liquid crystalline behavior in polymer liquid crystals are similar structural principles to the thermotropic non-polymeric mesogens. There must be the rigid part, and anisotropy in molecular shape which account for the existence of the liquid crystal mesophases in thermotropic non-polymer mesogens also apply to the polymeric materials. The macromolecules as a whole must either have a rigid rod-like, or disc-like structure, or contain mesogenic groups as monomer units in order to exhibit liquid crystalline properties. Liquid crystal polymers can be classified into two types: main chain and side chain liquid crystal polymers. There are two fundamental types of liquid crystal polymers. The left side in blue color is the main chain liquid crystal polymers. The mesogenic groups, circled in green, are located as a chain and connected through flexible segments called spacers. The spacers are circled in red. While, for the second type, the mesogenic groups are hung like pendants from the polymer backbone through spacer. There is no backbone in main chain liquid crystal polymers. The mesophase for liquid crystal polymers are similar to the liquid crystalline phases exhibited by the thermotropic non-polymer liquid crystals. Let's see first from the atomic level for polypropylene with degree of polymerization up to 10 to the power of 4. We view this polymer at the atomistic model. We can simplify the shape of the polypropylene as a string. Other than string, we can simplify other polymers' shapes to a D-block copolymer, where two blocks copolymer, the blue and the green blocks, within the same polymer causing macrophase separation. A star polymer. And a branched polymer. The bottom of the slide are the illustration how the strings assemblies in different phases such as isotropic, nematic, and smectic. For lyotropic polymer liquid crystals. The liquid crystalline phase is formed when the dry polymer is dissolved in solvent. As a result, fiber formation to give high tensile strength fibers. Two examples of main chain liquid crystal polymers are shown in this slide. The top example shows the mesogenic group circled in blue as in rod shape. In overall, the main chain liquid crystal polymers have repeating mesogenic units and connected with flexible alternating hydrocarbon spacers. This polymer will be in glass state at room temperature up to 65 degrees Celsius, then exhibits nematic phase from 65 to 135 degrees Celsius. The nematic phase is contributed by the rod shape of the mesogenic units. The second example is showing the main chain liquid crystal polymers with discotic cores, circled in blue, are separated by long flexible spacers. The long flexible spacers are responsible for the low melting point for the mesogenic behavior. Because of the discotic cores, this type of mesogen will exhibit columnar phase. In this slide show a few examples of main chain polymer liquid crystals. The most well-known example is Kevlar, reported by DuPont in 1970. Kevlar is essentially an aromatic polyamide based on aramid which forms a lyotropic nematic liquid crystal phase in fuming sulfuric acid. The box shows different types of mesogenic units for rigid, semi-flexible, and flexible polymers. Let's look at Kevlar as example of application of main chain liquid crystal polymer as a high-strength fiber. Kevlar is simply a super strong plastic. If that sounds unimpressive, remember that there are plastics extremely strong, lightweight and durable. Because of these, Kevlar is used in various areas. Find out more about Kevlar and application through the link provided on the slide. Let's see the structure and properties relationship for main chain polymer liquid crystals. There is a problem that normally will occurs when preparing main chain liquid crystal polymers. Mesogen with functional groups able to undergo polycondensation. To synthesis polyesters, polyamides, and polyethers linear main chain polymers. The direct, linear, rigid attachment of mesogenic groups often leads to problems. Low degree of polymerization, or less than 10. The melting point is quickly shifted to higher temperature with increasing R due to the high anisometry of the molecule, and the mesophase to isotropic transition temperature is also raised. Thus liquid crystal phase often cannot be reached in the case of oligomers in these polymers because the materials decompose before melting into LC phase. For example, let's see the polyester of 4-hydroxybenzoic acid. In polyester of 4-hydroxybenzoic acid, the mesogenic group is connected directly, linear and rigid. In order to overcome the problem, first, reduce rigidity by attaching the mesogenic groups via flexible segments. With increasing length of the flexible spacer between the mesogenic groups, both the melting point as well as the clearing point are progressively shifted to lower temperature. Increasing the alkyl or alkali chain length may lead to the development of higher-ordered smectic phase. Look at the polymer structure given on the slide. If the spacer, n, is increased from n equal to 3 to n equal 13. The transition of nematic phase to isotropic phase is reduced when the alkyl chain length increased essays. Based on the diagram, we can observe the odd-even effect. The length will influence conformation of the polymer, hence the clearing points. This approach has been adopted to produce a wide range of melt-processable aromatic copolyesters such as Vectra and Zidar. Second, suitable solvents such as concentrated sulfuric acid may be added to weaken the interaction between the rigid, rod-like macromolecules to reduce the melting point.